Okay, so this is 13.6, cylinders and quadric surfaces. So the idea here is we're going to be working with surfaces in space quite a bit, especially in the latter part of the class. So we want to get comfortable with them as soon as possible. And this section is kind of, the purpose of it is to give you a bunch of examples of surfaces, their equations, their pictures, so that we can actually have concrete examples to work with in the later sections. All right, so we're going to start with cylinders, which are going to be more than what you probably are thinking of as what a cylinder is right now. Let's get into it. So let's start with let's start in the plane. All right, just a regular XY plane, and let's draw a circle. So this is, let's say, x squared plus y squared equals 9. All right. Now, what we can do, before we actually move on, what do I mean when I say this, right? What do I mean when I associate an equation with a curve like this in the plane? Again, we talked about this maybe a couple times, but it's always good to repeat this just to make sure we're comfortable with what these kind of mathematical objects mean and how to interpret them. So when I say something like x squared plus y squared equals 9, most of the time what I mean is this is just shorthand for the points in the plane. Let me give this guy a name. The points x comma y in the plane where x and y satisfy the relationship x squared plus y squared equals 9. All right, so this is actually shorthand for this stuff on the right. Okay, so when I write x squared plus y squared equals 9, I'm actually talking about a collection of points, all these guys right here in the picture, a collection of points in the plane. Okay, and in this example, that collection would be a circle. Okay, so most of today, or most of this, well, all of this section is going to be writing down equations like this and then interpreting what they look like. Okay, so in the plane, this guy here, when I write down x squared plus y squared equals 9, that's a circle, that's a curve, right, which happens to be a circle. Okay, now what happens if I talk about the same equation now in space, right? I'm going to do the same equation in space. X squared plus y squared equals 9. All right, so this is going to be the collection of points, the collection dot 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 dot, right? Except now it's going to be x, y, and z. Okay, because we're in space. Dot 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 dot. All right, so now we're looking at all the points in space such that their x comma y comma z coordinates satisfy this relationship between them. Okay, now the kind of interesting thing about this particular equation is that you see no z's, and so the only relationship, only restrictions that we're looking at are between x and y. All right, so there is no restriction on z. So for example, if I have 1 comma square root 8, that satisfies, this is on x squared plus y squared equals 9 in the plane, right? Now in space, right, 1 comma square root 8, if I have this, right, it already satisfies the equation, right? 1 squared plus root 8 squared is equal to 9, right? So this z slot can be anything. All right, so what we have is, in terms of the collection of points, it's going to be it's going to be x comma y comma z, right? Where just x squared plus y squared equals 9, no restrictions. No restrictions on z, right? And so the picture is going to be, so in particular, it's going to be, for example, 1 comma root 8 comma 10. 1 comma root 8 comma 0, 1 comma root 8 comma 59, 1 comma root 8 comma 90, minus 97, right? Anything in this third slot will work. Okay, so if we draw the collection of these points, what we're going to have is if x, y, and z look like this, right? Then the points here, we have a circle of radius 3, right? Just as usual. But we're allowed to have anything, any z coordinate, as long as the x and y coordinates live on a circle of distance 3 to the z-axis. Okay, notice that x squared plus y squared is the distance to the z-axis squared, all right, in space. Okay, so it's going to look like this. It's going to be what we normally think of when we think of the word cylinder. All right, and it extends upwards along the z-axis and downwards along the z-axis infinitely. So it's actually an infinite cylinder. And it's a surface. It's two-dimensional in that if you're standing on the cylinder, right? So let me draw a little picture like this. If you're a person standing on this cylinder, right, how many different directions can you go and still stay on the cylinder? There's only two directions, right? You can go this way and stay on the cylinder. The opposite direction is just a negative of the first direction, so we don't count it as separate. And you can go this way, right? And the opposite is negative of that, right? Those are the two fundamental directions that you can move if you're on the cylinder and want to stay on it, right? Every other direction is a combination of these two directions, right? So this direction here is a, something, I guess, for this guy here, you move to the right a certain distance and you move forward a certain distance and you get the blue arrow, right? So because there's two foundational distance directions you can move and stay on the cylinder, that means it's two-dimensional. Okay, so that's a way to kind of visualize what it means to be two-dimensional or one-dimensional or whatever. All right, so one-dimensional would be, right, if you're a person here standing on a one-dimensional object, you only have one direction you can move. You can move this way, right, or the opposite direction, which is just negative of this way. So we don't count it as separate. All right, so this is one-dimensional because you only have one direction you can move in order to stay on that object. All right, in any case, this cylinder is a two-dimensional object. It's infinitely tall, and we're going to be working with things like cylinders quite a bit, especially when we get into integration, especially since we're going to be doing cylindrical coordinates as one of our topics. Okay, now, so that's a traditional cylinder, but for this class, we have a kind of a generalized concept of the word cylinder. So anytime we start with something in a plane, and right now I'm just doing XY planes. I'll do examples in a second where we do different planes. But anytime we start with something, let's say in the XY plane, let's say y equals x squared, right? So we start with a curve in the plane, like that, and we extend it to space, right? So let me try to draw that here, x, y, z. So that would be something that looks like this, right? Just drawing the parabola in the xy plane, just drawing it in space, all right? Now, if I look at the same equation in space, again, there's no restriction on the z, and so z can be anything. So as long as the x and the y satisfies the relationship that the y coordinate is the x coordinate squared, I'm gonna be in the collection of points that this guy describes. All right. So my z coordinate can be anything. So again, a way to kind of visualize this is you draw the picture in the plane. You draw it then in space, right? Just the curve, and then you extend it in the z direction. Okay, to mean that, right? Anything, x, comma, y, comma, anything, z can be anything. All right, so let me draw it kind of like this, and then we'll see kind of a problem when we do these pictures, right? And also downwards as well. Okay, So now we can see there is a problem. It's really, really hard to visualize if I do something like this. So you want to do some practice in terms of drawing pictures so that you can actually do some sort of filling in and still be able to recognize what what your picture is, right? So one thing we might be able to do here is reproduce this guy, the y equals x in the plane, reproduce it up here, right? Maybe reproduce it down there, like this. Now we can kind of more easily see that this is kind of like a curved thing going around in this way, right? So you definitely want to do some practice. What's going to happen oftentimes for these is these surfaces are a little complicated, and sometimes you want to draw multiple pictures, and maybe none of the pictures that you draw are completely satisfactory. But if you have all the pictures in front of you, whatever you're doing, maybe one of those pictures will help you with certain parts of your problem. Another of the pictures will help you with a different part of the problem, or something like that, right? So you don't necessarily need to have one picture that always works, okay? So in this example, maybe, for example, it'd be nice, it'd be a good idea to draw the picture like this, where I extend it like this and like this, right? And I just fill it in this way, right? Then it's perhaps a lot easier to see what the shape of this object is, right? So you don't have to necessarily try to draw the entire thing, okay? All right, again, here I'm implicitly, I'm not drawing the negative parts. I'm not drawing anything up here, right? But I do have an idea that this thing is basically like a parabola that's kind of extended vertically in the z direction, all right? Maybe you can even sometimes, draw a grid line or something like that. It might help you visualize this better, okay? And also, frequently, if you don't draw the parts that are obscured by your view, things will look more three-dimensional and, again, easier to visualize. Okay, so this is we still call this a cylinder. All right, so we still call this a cylinder as long as it's something basically like a curve in a plane that's extended outwards into a third dimension. We're going to call that a cylinder. Okay. Let me do another example. So so any curve in the plane we can do this for, right? Let me just do a random example, x, y. So if I just do something like that, right? Then x, y, z. Then this is something like, something like that. And if I were, if this had some equation, let's say y is equal to f of x, right, in the plane, then if I were to look at the same exact equation, right, in space, there's no restrictions on z, so I would be extending it upwards and downwards along the vertical axis. All right, so this would be, again, a plane. Maybe if I did this, it would look more three-dimensional. Okay, so any kind of curve I can do this for. Another one that we'll see quite common in this class is something where we start with ellipse. So let's see, maybe something like this, right, as opposed to a circle. So our first example was a circle. This one is going to be an ellipse. Let's say x squared over 9 plus y squared over 4 is equal to 1. We like to write ellipses in this way. So this is an ellipse centered at the origin, of course. We like to write it where there's a 1 on this side because it makes it easy to kind of visualize or to figure out what the axes are, right? For example, how wide is this guy? How tall is this guy? Well, the width is going to depend on this location and this location, of course. What is this location? This is when y is equal to 0, right? So when I plug in y equals 0, I get x squared. So y equals 0. I get x squared over 9 equals 1. And so x squared equals 9. And so x equals plus or minus 3. So this coordinate here is 3. That one's minus 3. Okay. On the other hand, these two are going to be where x is equal to 0, the y-intercept in other words. We get, well, when x is 0, the first term is 0, so we just get y squared over 4 should be equal to 1, which tells me y squared equals 4, which tells me y is equal to plus or minus 2. And so this is 2. And so this is -2, right? So this is an ellipse which is kind of, in a way, longer along the x-axis than it is along the y-axis, all right? So these are a good source of kind of examples for our class, which are not as simple as a circle, but not completely random and crazy, which will be kind of hard to work with. Okay, so the cylinder that corresponds to this is, again, once we've drawn the picture in the plane, again, we're just doing the same procedure over and over again. We extend it into the z direction. So maybe this time I'll draw it kind of like this, right? And then let's extend it this way like this, and let's draw that there. And then maybe, again, sometimes if you draw a grid, you can more easily see what's going on. Maybe if I draw the inside of this like that, it looks more three-dimensional, and then maybe some curves in here, right? So you can see it's kind of like a, well, it's an elliptical cylinder, literally. All right. Okay. So a lot of the source of the surfaces that we're going to be playing with are going to be cylinders, especially when we start to do stuff like integration. All right. Now, so far, all our examples have been cylinders where we start with something in the xy axes, and then we extend it out to z. But of course, you can certainly do it, for example, in the xz coordinate first. So let's say we have, let me draw something in the xz, right? Let me just draw a traditional cylinder, right? X squared plus y squared equals 1, right? So this is a circle. Now I can, sorry, that should be a z, right? So this is a, in the xz plane, if I just have the two coordinates x and z, this guy would be a circle. But if I add the y coordinate, right, and I look at the same exact equation, then again, the idea is that this equation represents all the points, x comma y comma z, that satisfies, where the coordinates of the equation satisfies the first coordinate squared plus the third coordinate squared equals 1. And because there's no mention of the second coordinate can be anything as long as the first coordinate and the third coordinate satisfy the appropriate equation. And so that means, right, you take the picture again in the xz plane this time, and then you just extend it along outwards, pull it out, extrude it out towards the y-axis. So something like that, right? And let me do it backwards as well. So we're just pulling out along the y-axis, okay? And of course, if you do the same thing with y and z, so this is getting maybe a little repetitive now, so this will be our last one of this type. Let's see, something slightly different. So this is z equals y squared, cubed, right? If I now look at it, maybe I should separate those two examples. If I think about the same equation except in space now, it's going to be, there's my yz plane, looks something like that, right? And then I'm pulling it out along towards the z-axis. Sorry, toward the x-axis, right? So I'm extruding it out towards the x-axis. So something like this, and then something like that, right? Where this looks like that. Okay. All right. Not the best picture, actually. Kind of terrible, actually. Let me fix it. So this, right? These two kind of views should be identical in this way. And then it goes downwards. I guess over here it's going to be maybe like that. That looks a little better. All right. So again, don't be afraid. I mean, we're definitely not used to drawing these things a lot, or looking at these in perhaps drawing these in everyday life. So don't worry if your pictures look a little raw at the beginning or even towards the end. As long as you can kind of tell what's going on, you should be okay. All right. So those are cylinders. let's now talk about a few other surfaces in space. Again, the word surface, when we say surface in space, we mean a two-dimensional surface, all right? If we use the word curve in space, we mean a one-dimensional object in space, all right? So curve is always one-dimensional. Surface is always two-dimensional, all right? So we would never talk about surfaces in the plane because, well, the plane is already flat, so there's not actually much to talk about there. Okay, so let's talk about, so the rest of this section is going to be kind of a I guess technically it's called quadric surfaces, so we'll be looking at quadric surfaces, so surfaces that involve x squares, y squares, and z squares. And we'll just look at a whole bunch of examples of these and some of their pictures and how to view them or analyze them. All right, so the most basic one is x squared plus y squared plus z squared equals 9, something like this. This is, we've already talked about this a little bit. This is a circle, right? Radius 9. Maybe if I draw this, it looks a little better, or maybe worse. If it's worse, just erase it and, draw it again. And just draw, the parts which are relevant, right? Maybe just the equator. Already I can get a okay picture of what's going on. All right, so again, this guy is a sphere because the kind of a really good way to think of this is distance to origin squared is equal to 9, right? And so this is saying distance to origin equals 3, right? So this is the set of points, x comma y comma z, whose distance to the origin is always 3, is exactly 3. And so of course that's going to, if you take the collection of all these points, it's going to turn out to be a sphere about the origin. Okay, we've also talked about the fact that you can modify these, right? So x minus 3 squared plus y squared plus z plus 4 squared equals 25. This is going to be sphere center 3 comma 0 comma minus 4 radius 5. Okay, so it's pretty much the same idea as in working with circles in a plane, except you've got the extra z coordinate. All right, let's get more complicated. X squared over 9 plus y squared over 4 plus z squared over 16 equals 25. Right, this guy's going to be an ellipse. Oid. All right. So the basic, basically it's the analogy of the ellipse, or one analogy of the ellipse in 3 dimensions. And again, if you just do the same analysis we did with the ellipse earlier, you'll notice that when x and y are, sorry, let's say y and z are 0, then x is going to be, so let me actually do just one of those. So when y, z equals 0, in other words, we're looking for the x-intercepts, right? We have x squared over 9 is equal to 25, and so x squared is equal to, I probably should have done a 1 here just to make things a little nicer, but it doesn't matter, is equal to 9 times 25, and so x is equal to plus or minus 3 times 5, which is plus or minus 15, right? And so this point here is 15, that point here is minus 15. All right, and so in the same way, you can kind of plot out what the y's are. It's going to be a little smaller, and then the z is going to be a little taller, right? And so this is going to be an ellipsoid, kind of like that, right? So it's like an oblong, a sphere, basically a sphere where you've stretched the axial directions non-uniformly. Okay. All right. Let's see. Okay. So you can do the same modifications. If I go x minus 1 whole thing squared, then what I've done is I've shifted the center of my ellipsoid to the right, sorry, in the x direction by 1 step. Okay. All right. There's a concept that the book calls the trace of of a surface. It's not standard terminology, but I guess we'll try to keep with the book on this. It's kind of minor bit of terminology anyway, so it's not a big deal. So what this is the intersection of a surface with the coordinate planes. So what I mean by that are the xy plane. So this is all happening, of course, in space because we're talking about a surface. The yz plane and the xz plane. Okay, so it's just the intersection of a surface with the three coordinate planes. So we would say, for example, or at least the book would say, the xy trace. That would be the intersection of my surface with the xy plane. All right. So for example, the xy trace of this ellipsoid up here is going to be what I get when I, well, the intersection with the xy plane is going to be where z is 0, right? Because the xy plane is literally z equals 0, right? The equation of the xy plane would just be z equals 0. So if I have, let me actually work down here. So trace of, let me just write down a concrete example. X squared over, I guess I should just use the one up there. X squared over 9 plus y squared over 4 plus z squared over 16 equals 25. And let me write using the same notation as the book. So xy trace of this, right? This is going to be, is by definition, right, intersection of x squared over 9 plus y squared over 4 plus z squared over 16 equals 25, and z equals 0. All right. So a good way to think about intersections is you're on the intersection of something. So you probably thought about this when you did the homework from chapter 13, right? The intersection of something, of two, in this case, surfaces, is going to be the set of points where that live on both surfaces, right? So it has to be points that satisfy the first equation and satisfies the second equation. Okay, and if you satisfy that, in this case, it's going to be simple because if you satisfy the second equation, we automatically know z is 0. And so it turns out that this is going to be the set of points where you have x squared over 9 plus y squared over 4 equals 25, and of course z equals 0. All right, and that's nice because we know what this guy exactly looks like, right? This is going to be ellipse. Let me emphasize this is and, right? We have to have the z coordinate equal to 0. And so this is going to be an ellipse in the xy plane. All right. So in terms of visualizations, right, if you had your ellipse, let's say we drew our 3D ellipse, the full 3D picture. So let's say it looks something like that, right? The trace, the xy trace would be, if you cut the ellipse using the xy plane, right, what would the cut be? It would be exactly this guy right there, right? And its formula would be x squared plus y squared, x squared over 9 plus y squared over 4 equals 25, comma z equals 0, all right? Okay, so the xz trace, right, is going to be, well, pretty much self-explanatory in terms of the picture. Is going to be the intersection of the xz plane with my ellipse, or my ellipsoid, right? So it's going to be something that looks like that, right? I think z, let me see, z over 16, so that guy is going to have the longest radius. So yeah, it's going to be like a tall ellipse like that. Okay. All right, intersections of surfaces with the planes. So these traces are going to be pretty useful when we start to do integration. We're going to want to know what these guys look like because they're often going to be regions of integration for us. So that's going to be something that's a lot more complicated in multivariable integration compared to one variable integration, in that the regions of integration could be very wild, much more complex than just the simple intervals in one variable calculus. All right. By the way, when we do these intersections, so for example here, the intersection of the ellipsoid and the plane, we generally do get a surface. I guess I talked about that in one of the lectures last week. This is two-dimensional. Let me put this here. This is two-dimensional. This is two-dimensional. In total, we're in space, so we have 3 dimensions. So we expect the intersection to be 2 plus 2, 4, minus 3. We expect it to be one-dimensional. And in these examples, we see that that's actually the case, right? The intersection here is a ellipse living in space. Over here, the intersection is an ellipse living in space. All right, so a curve living in space. But again, just remember, not always necessarily the case. All right, there's always exceptions to this general principle in red over here. Over here. All right, so it could be one-dimensional. It could be just a point, for example. It could be two-dimensional. All right, it can't be three-dimensional for sure. All right, because it's an intersection, so it has to be smaller than or equal to each of the 2 individual pieces. All right, let's look at another equation. So again, this section is mostly just a mishmash of equations. But again, these will form a lot of the examples that we're going to be working with later on in the class. So you definitely want to get comfortable with each of them. All right, so z equals x squared plus y squared. So this is a really, really common one that we'll see. So what is this? The best way to look at this is always remember, and we'll talk about this quite a bit when we get to polar or cylindrical coordinates. X squared plus y squared is distance to z-axis. Right, so in the plane, it would just be distance to the plane, right? But now since we have a z-coordinate, it's actually distance to the z-axis. Okay, so this equation here, z equals x squared plus y squared, is saying we're looking at all the points where z is equal to distance to z-axis squared. All right. Okay, so if we think about, let's give this guy a name, distance to z-axis. So distance to z-axis, let me call that r, right? And we'll use the same r, of course. It's the same r. This is literally the same r, not literally the same, but the same idea as the r from polar coordinates. And we'll use this r in cylindrical coordinates as well. So this r is in space. We would use it as distance to the z-axis. Okay, not distance to the origin, distance to the z-axis. All right. Okay, z equals r squared. Right, that's what we have. So let's think about r. Let's think about z. Let's think about these 2 coordinates. All right. So z is equal to r squared. That's what we got. What's the picture of that? That's a parabola. Oops. That's just a regular parabola in terms of a z and the r axis. All right. Okay, so why did I draw this? Well, when you have a situation like this, this is distance to the z-axis. So if I were to kind of draw a picture in space, right, every point, let's say around this ring here, right? Every point on this ring has the same r value, right? Because every point here is the same distance to the z-axis, right? That's these dotted lines here are the distance to the z-axis. Okay, so what's going to happen is every point on this ring here or on this circle here will have the same height when we think about z equals x squared plus y squared, right? Because every point here, their x squared plus y squareds are the same number. And so the height of this ring, or this, I guess, let me just say this ring, is going to be that r squared, right? So if I draw another ring, at a different height, it's going to have, for this particular surface, the same height, right? And what is it going to be? It's going to be like a parabola like that, right? So all of these guys right, are circles, if you look at its shadow of this guy here, for example, down to the xy plane, it's going to be a circle, right? So every point on this circle down here is the same distance to the origin in this case, right? So every point here is going to have the same z height because we're demanding that z equals x squared plus y squared, all right? Okay, another way to say this is if we take the z-r axis and we draw our picture, right? If we were to satisfy z equals r, then we would just rotate this r and then make a surface of revolution. And that's actually going to be the surface that we're talking about. Okay. All right, so these surfaces of revolutions, a lot of our examples are going to be surface of revolutions like this. Okay, so this is a paraboloid, right? Because it's essentially an extension of the idea of a parabola from the plane. Okay, of course, we can do variations of this. We can shift it around by adding things inside here. So x minus 3 whole thing squared plus y plus 4 whole thing squared, right? That will shift the center of this paraboloid, around along the xy plane. Okay, and of course you can also do other modifications, just like we did in one variable calculus, or maybe earlier than that, right? If we start out with this, we have a paraboloid, right? Then if I did something like this, equals x squared plus y squared plus 9, right? Then this would be, everything would be shifted up by 9 steps, right? So remember all those kind of graphing things that maybe you learned, I guess probably in high school, right? So they apply whenever you have kind of a z as a function of x and y. That's roughly what's going on here, okay? Pretty soon we'll actually put that more formally. Z will be a two-variable function of x and y. Okay, but the same ideas apply. If you add a 9 like this out here, you're going to be shifting it up and down. If you add things inside, like z equals, just like I said, z equals x minus 3 squared plus y squared, that's going to shift this thing in the x direction by 3 steps. All right. If I go z equals minus x squared plus y squared, right, that's going to flip it upside down. Right, just like the situation in the plane. And if I go z equals 9 minus x squared minus y squared, that's going to be, I flip it upside down, I move it up 9 steps. Okay. So that kind of stuff is hopefully you're pretty comfortable with. We'll definitely not always be looking at kind of the super simple z equals x squared plus y squares. You'll see in the homework there's a lot of kind of these modifications that you might need to play with. Okay. Let's see. Other variations of this, we can do x equals y squared plus z squared, right? And just as before, x is now a function of y and z, right? X depends on y and z. And so we're going to have a paraboloid that comes out this way with the kind of the center axis being the x-axis as opposed to the center axis being the z-axis, right? And of course, y equals x squared plus z squared is going to be one where the center axis is along the y-axis. All right, and we'll definitely be working with these kind of laying down paraboloids or whatever objects quite a bit. All right. Okay. Let's see what else we got. Z equals x squared over 9 plus y squared over 16. Right. So one way you can look at this is for every fixed z number, right? If z is equal to 1. Then the right-hand side, then the equation is going to be the equation of a paraboloid, right? X squared over 9 plus y squared over 16 equals 1, right? If z is equal to 10, you're going to have another paraboloid. 10 is equal to x squared over 9 plus y squared over 16, right? But because of that 10, it's going to have a bigger radius, right? Or bigger, it's going to be a bigger paraboloid. And if z is equal to a half, then you're going to have a smaller ellipsoid, right? So what this picture is going to be is ellipsoids. Let's see, so this is 9 and 16, so it's longer in the y direction. So maybe something like that, right? It's going to be like a paraboloid based on an ellipse, elliptical paraboloid. All right. And again, as we get higher and higher and higher in terms of z, right, this number on the left-hand side is going to be bigger and bigger and bigger. And so the radius, the two, I guess I'm just going to say radius, the two major and minor axes, I guess that's the technical term, are going to be bigger and bigger and bigger. So these ellipsoids, these ellipses get bigger and bigger and bigger. Okay, just like with the paraboloid, right, the circles get bigger and bigger and bigger as you go, I guess I should do this one, as you go up along the z-axis. Okay. All right. Let's see. Z squared equals x squared plus y squared. And you'll notice all of these are quadratics because, or, you know, degree power 2 surfaces. These are nice and simple. They're a really good set of examples that that are simple, relatively simple. They're just, you know, polynomials degree 2 in multivariables, of course. But they show us a lot in terms of features, diversity of features. So they're a really good set of examples. Okay, so this guy here is, let's see, we've got the x squared plus y squared again. So this is distance to z-axis, right? So and again, let me call that r. So we've got z squared is equal to r squared, which tells me z is equal to plus or minus r, right? What is that? If I just drew it in terms of r and z, that would be like that, right? So z equals r would be this. Z equals negative r would be that. And we've got both, right? Z could be positive r, it could be negative r, okay? Because, again, if z is equal to 3 and r is equal to minus 3, z squared equals r squared, right? If z is equal to minus 3 and r is equal to 3, z squared is equal to r squared. So all the points that I've drawn are on this curve, okay? Right now, if I revolve this about the z-axis, I'm gonna get cone, or a double cone, I guess. All right. Okay, so this is a nice source of examples because a cone is nice and simple in terms of its surface. It's not curved or anything like that, right? It's just a kind of like a flat cone in a way. And it also has this really interesting point at the origin where things are in a sharp corner. Okay, so that's a good source of examples. Okay, let's see. Of course, you can do variations on this. Z squared equals 9x squared plus 16y squared or something like that. And then you'll get kind of an elliptical cone, right? I guess I've been doing mostly examples where I divide. So let me just keep it a little consistent just in terms of the examples, right? Of course, if I did put a 9 here, then it would make it so that the minor axis would be really small, all right? Because it would be the same thing as as putting 1/9 underneath. Okay. All right. Those are the core examples, at least let's say for now. There's a couple more that I'm going to talk briefly about. We'll see more about them in the future. But I've tried to make most of the homework problems about these ones that we've seen. Just want to try to keep things relatively simple for the class, right, in general. And we don't really need the more complicated ones at the moment. So I don't want to talk too much about them. But I certainly want to mention them. So z equals x squared minus y squared. So most of the ones all the ones we've seen, right, basically are going to be x squared plus y squared, right? If you look at the examples we've done, or, you know, something x squared plus something y squared. This guy is really, really different because of the negative sign, right? So a lot of the analysis we've done where x squared plus y squared means distance to the z-axis, but x squared minus y squared is not going to be distance to the z-axis, right? So things are a lot more complicated for this. This is a hyperbolic paraboloid. So you don't really have to know these names necessarily. But the really interesting thing about this guy is the picture, which is not so easy to draw. But the idea is it's a saddle. So like this. Let me draw it like this. Right, and this, of course, extends downwards, and this extends upwards. This extends upwards. Right. So the idea is this is a saddle. All right. So this is probably the most interesting of the surfaces we've looked at this point. And we'll definitely look at more examples. You'll definitely see this function or this this surface in the future because it has a really interesting point right there at the origin. Because at the origin, if you're a ball sitting at the origin, right, you're kind of at a low point because of this, right? But then you're not at the lowest point because you can roll downwards this way. Okay. So it's like kind of like a mountain pass, but it's interesting because it's an unstable equilibrium. All right, and it's kind of analogous to in one variable calculus y equals x cubed, where you have a critical point right there, but it's neither a max nor min. Max nor min. Oops. Nor min, but is a critical point, right? And so this guy here, this saddle, we usually call that a saddle point, is pretty much an analogy to the y equals x cubed situation. All right, but as you can see, things are a lot more complicated in the surface case, which is why we're going to be spending quite a bit of time studying this kind of stuff when we get to multivariable functions. All right, by the way, this is called a saddle because it looks like a saddle, right? I guess if we had a horse, it would be something like that, right? Hopefully this gives you a perspective on the picture. Okay. Let's see. So I'm not going to do too much with this right now, except just introduce a picture. Let me just draw one more kind of weirdish surface. Squared plus y squared minus z squared is equal to 1. And of course, you can see this in many different variations. X squared plus y squared minus 1, or z squared plus 1 is equal to x squared plus y squared. This one is perhaps not as weird because, again, this is our favorite thing, our r again, right? And so this guy is a rotation of, so one thing you can do, right, you can graph this again. This is r, this is z. It's going to look something like that, right? Two of them, because we've got the z squared. So how do I know it looks like this? Use your one variable calculus graphing skills, right? So you can think of, I guess this is getting a little messy here. Let me circle this right there. You can think of, if you want to think of this in terms of z and r, this is, as we have been doing, z squared plus 1 is equal to r. So you think of this as r being a function of z. And so you could graph this, right, using the graphing techniques from one variable calculus. And you would find that it would have a critical point right there. Right. Again, maybe you would, normally when you think about this, it would be tilted like this, z and r, right? And you would graph like that. You would have a critical point right there, a minimum point right there. It would be concave up. If you take its second derivative, the whole thing is always concave up. So it looks like that, right? So that's how you get this picture. And of course, you have this picture on the other side. When you do a rotation, you're going to end up with something like this, all right? And it makes sense because, for example, if I look at this guy here, when z is equal to 0, I get x squared plus y squared equals 1, which is a circle on the xy plane, right? And as I move upwards, away from upwards towards the z-axis, I have x squared plus y squared equals something that gets bigger and bigger and bigger as I go up along the z-axis. And so I expect these circles to get bigger and bigger and bigger and bigger, right? And the shape of how fast it's getting bigger and bigger and bigger is determined by this curve right there, all right? This one we're not going to work with too much. At least it's not necessarily perhaps as interesting as some of these other ones, especially because it's not in the form of a function, right? And if I did put it in the form of a function, it would be z equals square root x squared plus y squared minus 1. And square roots make things really unpleasant. Whereas, for example, this one above, the saddle, z equals x squared minus y squared, it's like a function, right? And that's why it's a good source of examples, all right? Because if you do think about this a little carefully, that's a saddle point right there as well, right? It's got kind of this direction here where you're moving upwards in quotes, right? And this one where you're moving downwards. So it does have the similar situation where you have a saddle, but again, it's not easy to work with this when you want to describe it as a function. So we're not going to play with this guy as much. And I tried to avoid this guy in the homework as much as possible. Okay, let's see. So maybe one last example, and we're all set. Again, this section is just to kind of get us set for working with more complicated surfaces in the future to allow us to actually study functions in two variables, especially, and to help us study surfaces in space. Okay, so last thing is you'll see on your homework something like they perhaps maybe want you to identify a certain surface from its equation, x squared plus y squared plus z squared plus 4x equals 10, right? This doesn't look like any of the examples that we've written down, so it's not necessarily that immediate to identify because of this 4x, right? But remember, always remember that you have the technique of completing the square. And so if you do that, this 4x is going to disappear. It's going to be absorbed into a square term for the x, and then you're going to have a sphere, right? So x squared, let me write it like this, plus 4x. And then I'm going to complete the square by adding 4, subtracting 4, plus y squared plus z squared equals 10. And then the point of adding and subtracting 4 is these guys go together. X plus 2, whole thing squared, minus 4 plus y squared plus z squared equals 10. And so ultimately you end up with x plus 2, whole thing squared, plus y squared plus z squared is equal, that's a 10, sorry about that, equals 14, right? So ultimately it's a sphere, center minus 2, 0, 0, and its radius is square root of 14. All right. So you'll see some problems in homework where things don't look exactly like what I've shown you or what you might see in the text of the book, but just keep your mind open about all the techniques that you worked with in high school in terms of looking at graphs of functions, right, and the techniques you had there. Okay. I think that's it for 13.6, and we'll do 14.1 and 14.2 in a separate lecture.